This is going to be a video on section 2 of chapter 7, which is about looking at similar triangles and their mostly algebraic properties for now. So, we know that when polygons have all their corresponding pieces congruent to each other, they're called congruent. So again, if there's a way I can match up every side of this first polygon, which is a triangle, to every side of the second polygon, then I know that they're congruent. If I were to overlap these two shapes, this polygon right here, if I were to overlap that with this polygon right here, there's a way I can do it that they would be overlapped exactly and then everything would match up perfectly. So that's called a congruent polygon. Well, we're going to be looking at similar polygons. So similar polygons are polygons that are not exactly congruent, obviously, but that there's some sort of ratio, some sort of multiplicative or division value that you can do to go from one to the other. There's a constant multiplier or a constant divider. Like for example, in this one here, if you look at the corresponding pieces, again, corresponding pieces are pieces that like in the same location. So this is the hypotenuse, right? This is 15. That's the hypotenuse. It's across the right angle. This 5 is also the hypotenuse, because again, it's across the right angle. Well, obviously these hypotenuses, are not congruent. But if I take 5 times 3, I get 15. And if you look at the bottom edge here, 3 and 9, those are corresponding because they're both on the same position. They're both between the right angle and the double arc. If I take 3 times 3, I also get 9. So 5 times 3 is 15, 3 times 3 is 9. So you can probably guess that this missing side here is going to be 4 times 3, which means that this missing side here would be 12. So each of that, if I call this polygon A and polygon B, we could say that polygon A times 3 is equal to polygon B. Every side on polygon A, if you triplet, gets you polygon B. Now, normally we would just say that, polygon B is 3 times as big as A, or you can say that polygon A is 3 times smaller than B, because you could do this the opposite way. You could say B divided by 3 is A. If I take 15 and divide it by 3, I get 5. 9 divided by 3 is 3. 12 divided by 3 is 4. So that's what a similar polygon is that there's a constant multiplier from one to the other. And again, the key thing is it has to be constant. Like if this was an 8 instead, I couldn't do this because 3 times 3 is not 8. It has to be a constant multiplier between all the sides of the polygon in order for it to be similar. Now, that multiplier is called the scale factor. That scale factor can go one of two ways, depending on what you start with and what you're ending with. So the wordplay here is kind of important. So it says here that ABC is similar to XYZ. So this little squiggle here means similar. Now, if we look here, okay, ABC, so AB should correspond with XY. So AB, 6, corresponds with XY, 3. Just like with congruent polygons, the labeling is important. So if I want to say the scale factor from XY to AB, that would be 6 to 3. So the scale factor is kind of written backwards. So if I say XY to ABC, that means that AB is the one that goes on top, the 6, and the XY is the one that goes on bottom, or the 3. Because again, what this is saying is, what do you have to do to this triangle to get to this triangle? And as we can see here, that's a timesing by 3, or timesing by 2. 3 times 2 gives me 6. Okay? That's the scale factor that way. Now, if I say the other way, what's the scale factor if I want to go from ABC to XYZ? That would be 1/2, because 6 times 1/2 is 3. Again, in this case, the ABC is the one that goes on bottom, and the XYZ is the number that goes on top, and that gives me 1/2. So the scale factor is what you multiply by to go from one triangle or one polygon to another if they're similar. And again, the order of the scale factor matters because it's about what you do to go from one to the other. Again, it takes a little time getting used to, but that's what we're going to practice and make sure we can get that down straight. All right, so determine whether the triangles shown are similar. If so, write the similarity statement and the scale factor. So basically, this is just kind of practicing our labeling. So first off, are these polygons similar? Well, let's check. This 12.5 is between the single arc and the double arc. This 10 is between the single arc and the double arc. So those two should be corresponding. So one way we can tell if they're similar is we can just match up their sides and see if we come out to the same fraction. So let's just go ahead and do that here. So we're going to take 12.5 over 10. Now, if they're similar, this fraction should come out with the same decimal or reduced fraction as all the other corresponding sides. So, for example, 11.5. That's between the double arc and the non-arc. So that is going to correspond to 9.2. So now I did 12.5 over 10, so now I'm going to do 11.5 over 9.2. I have to be consistent into how I construct my fraction. It has to be a consistent setup. And then lastly, this 15 is between the single arc and the non-arc, so that'd be 15 over 12. Now what I'm going to do is I'm going to take these fractions and reduce them all or get them down to a decimal and see if it comes out to be the same number each time. So if we take 12.5 divided by 10, that's 1.25, 1.25. Then if we take 11.5 divided by 9.2, that's 1.25, looking good so far. Now in order to be similar, these all have to be the same. These ratios all have to be the same. 15 divided by 12, 1.25, 1.25. So this would be a similar polygons a pair. These two polygons would be similar because when I take their corresponding sides and I match them up, I get the same decimal each time, which means I have a consistent scale between them, which is required for similar polygons. Sorry. So the way I would write this is I would write, say, triangle NQP. Now, I have to be careful how I label this, right? Single, double, non. That's how I went, right? NQP, single, double, non-arc. Well, that would be similar to, same method here, single, double, non-arc. So that'd be R, S, T. And then it asks me what the scale factor was. So if I label it this way, I could say that the scale factor going from NQP to RST. Am I going from a bigger one to a smaller one, or a smaller one to a bigger one? Well, this triangle is bigger because all the sides are bigger. 12.5 is bigger than 10. 11.5 is bigger than 9.2. 15 is bigger than 12. So I'm going from bigger to smaller if I'm going in this direction, right? NQP to RST is bigger to smaller. So I'd say the scale factor is dividing by 1.25. If I take 12.5 and I divide it by 1.25, I get 10. Just to prove that to you here. 12.5 divided by 1.25 is 10. 11.5 divided by 1.25 is 9.2. Now, I could say the scale factor is also multiplying by 1.25 going the other way. So this scale factor is going from NQP to RST. If I want to go the other way, it would just be simply multiplying by 1.25, which, again, you can write as a fraction as well. You don't necessarily need to write it as a decimal, but you can write these as fractions too. But that's how scale factor works, is you divide by the scale factor to go to the smaller one, you multiply by the scale factor to go to the bigger one. Or I shouldn't say that, because if your scale factor is less than 1, then it can be a little bit wonky. But basically, you want to make sure that your numbers are increasing or decreasing depending on which one you're going to. If I'm going to a smaller fraction, or going to a smaller triangle, I want to make sure my numbers are decreasing. If I'm going to the bigger triangle, I want to make sure my numbers are increasing. Now, one of the requirements for being similar is this, like we just did there, right? We have to have all the sides have a matching ratio. They all have to have a matching sort of scale with them. And again, I could flip all these and it'd be the same, by the way. I could do 10 over 12.5, 9.2 over 11.5, and 12 over 15. It wouldn't be the same number, but they'd all be consistent. So the key thing here right now is that when I have sides and I match them up, they all get me the same number. Then I know that they're similar. Well, another way that might be slightly easier is something called the AA theorem, which basically says that if you can get two angles congruent, or if you know that two angles between the triangles are congruent, then the triangles are similar. So that's all you need. If they mark two angles congruent like they did here, I could instantly tell that these are similar because they have two matching sets of angles, two matching angle pairs. That's kind of a shortcut to knowing that they're similar. And again, it comes from this idea of the third angle theorem. Basically, for any polygon, if all the angles are similar, or sorry, if all the angles are congruent, then we have the similar polygon. Well, for a triangle, because of the way the angles work, you only really need two, because if you have two angles, you know the third angle has to be congruent because of the third angle theorem. So it just kind of boils down to this AA similarity theorem, which is if you have two congruent angles, then the triangles are similar. Two congruent angle pairs, I should say. So like in this case, we instantly know, hey, these triangles are similar because they have two matching angle pairs. Now, we want to find the values of these variables here, obviously. So it's going to be a little bit trickier, but let's see if we can match this. So first thing we need to do is find a scale factor, my SF. We'll call it SF, scale factor. So in order to find the scale factor, we need a matching pair of numbers that we can create a fraction or a decimal out of. Well, let's look at 4 here. 4 is between the single and the double arc, so 4. 2 is between the single arc and the double arc, so 2. So 4 over 2 is 2. And this is going from JML and JML and QTS. So my scale factor here is 2. I'm going to divide by 2 if I want to go from the bigger one to the smaller one. I'm going to multiply by 2 if I want to go from the smaller one to the bigger one. I'm actually going to write this as 2 over 1 just to show you something here. So the way I would find x is I'd start with my scale factor, 2 over 1. Set it equal to another fraction. Now, when I made my scale factor, let me mark this as triangle A and triangle B. When I did my scale factor, I did triangle A over triangle B, right? 4 was from triangle A, 2 was from triangle B. I could create another fraction here using the same method, triangle A over triangle B, and that should be the same as 2 over 1. Like, for instance, if I take 6x minus 3, 6x minus 3, over, let's see, double to non-arc, that'd be 3, over 3, this should come out to be 2 over 1. Again, just like we did back here. All of these fractions came out to be the same decimal. This came out to be the same decimal. This came out to be the same decimal, which means that this 6x minus 3 over 3 should come out to be the same quote-unquote decimal or fraction, such as 2 over 1. So when I have it set like this, I can then cross multiply and solve. So cross there, we get 6x minus 3 is equal to 6. And then we just do our quick little algebra here. So we get 6x is equal to 9. Divide by 6, divide by 6. I get x is equal to 3 halves, or 1.5. We want to do it that way. So that's one way of setting this up here, is to get your scale factor and then just simply use this scale factor to solve all your other missing sides. Like if I want to solve for y, I would do the exact same thing. I'd start with 2 over 1, and then make sure that my fraction here is done in the same order. So once again, when I made my scale factor, I chose to do a over b, first triangle over second triangle, which means when I make this fraction, I have to follow that same pattern. So this again is in the first triangle, so that's going to go on top. Its partner, let's see, single to non-arc, that'd be 5. Its partner is going to go on bottom. And then I'm going to cross multiply. So I get 3y minus 2 is equal to 10. Add 2, we get 3y is equal to 12. Divide by 3, get y is equal to 4. So that would be probably the most direct and I think easiest way of solving these, is to simply make your scale factor first. You should have one number pair to start off with, right? You should have one number pair to kind of get the ball rolling. We'll talk about harder problems when we don't have that later on. But get your scale factor, make sure you remember the order in which you did it in, and then simply use that as your key to set up a cross multiplication problem for all your other missing sides there. So let's try a few more here for quick practice. We don't necessarily do all of these, but we'll try them out. So this one here, again, we know that these are similar because they have matching angle pairs, so we don't need to worry about checking that. We first need to find out a good matching angle, or a good matching side pair that we can make a scale factor off of. Well, I see here that 6 is a triple and double, so 6 is between the triple and double arc. 4 is also between the triple and double arc. So again, I'm going to label this A and B. So I could set this up as 6 over 4, A over B, reduces down to 3 over 2. So that's my scale factor, my SF, 3 over 2. So if I want to solve for x, 3 over 2. Now remember, this is 6, which is from A, and 4, which is from B. So this is going to be equal to A's triangle over B's, or A side over B side. So if I want to solve for x, x is between the triple and the single arc. 7 is also between the triple and the single arc of triangle A. So it'd be 7 over x. Remember, 7 goes on top this time because I want A over B, and 7 is a part of triangle A. Then you cross multiply, you get 3x is equal to 14, and you get x is equal to 14 thirds, or whatever that fraction, or whatever that decimal would be if you want to put it as a decimal. Ditto for y, okay? If I want to solve for y, I still start with 3 over 2. Y is between the double and the single. 8 is between the double and the single. Therefore, it's going to be 8 over y. And again, the 8 goes on top because I did triangle A over triangle B. Therefore, 8 has to go on top. Do some quick cross multiplication. You get 3y is equal to 16. And then you have y is equal to 16 thirds. So again, the order in which you make your fractions is key. So make sure you mark down on your scale factor what order you did it in, so you make sure you're consistent with your problems. Same deal over here, right? So I think I might have cut off my segment there, which is unfortunate. But if I want to set this up here, let me actually zoom out real quick, just because I think I did mess up my segment there. Well, nope, maybe I didn't. My bad. All right, so now I messed that up. That's unfortunate, but we'll just go with this double vision here. So I have these triangles here that I need to set up a scale factor for. Let's see. Well, I know that single and double here, right? And 7x is also between the single and double. And again, I apologize if this triangle got moved out, but we'll just deal with it right now. So I know that these two things are going to go together. So it's going to be 5x plus 2 over 7x. Again, I'll mark this as triangle A and triangle B. We'll just do it that way. Now, in this case, it's a little bit weird, but I saw what I did. Let me see if I can't adjust this real quick. So give me one moment here to try to readjust this triangle here. There we go. It's a little bit better. Okay. So the reason that it looks a little bit off is because if you notice, this 28 is between the right angle and the single arc. Well, this 21 is also between the right angle and the single arc. So these triangles are similar. It's just that this one's a little bit twisted out of shape in terms of orientation than the first one. That's why the angle markings are so important. So in this case here, 21 would go on top because I'm doing, again, this is A over B, right? So it'd be 21 over 28 on bottom. Now, again, I could reduce this if they have some common factors in it, but I'm just going to leave it like that just to use my calculator here. But again, the order is important and the matching is important. So double or single to double, 7x and 5x plus 2, right angle to single, 28 and 21. And again, A over B, A over B. So then you cross multiply. Now remember, when you cross multiply this over here, you have to make sure you multiply to all the terms in here. So it's like 28 times 5x, which would be, let me just do that in my calculator real quick just so I don't risk getting the numbers wrong. So 28 times 5, which is 140, so 140x, plus also 2 times 28, which is 56. So remember, this 28 gets multiplied to both of these terms, not just the first one. You're basically distributing it to the top. And over here we have 7 times 21, which is 147x. You subtract 140x from both sides, so subtract 140x, subtract 140x. We end up with 56 is equal to 7x, divide by 7, and we get 8 is equal to x. So again, make sure you pay attention to how the angles are marked here, because they can be twisted a little bit, and it makes it hard to kind of match up, especially when it's kind of deceptive like this. Okay? So the order to indicate fractions is important, and the numbers you pick are also important. So use the angle marking. Sorry about that. My mic cut off there. My apologies. Let me just double check that's still going. Okay, good. All right. So remember, this also holds true for perimeters as well, and also for non-triangle polygons. So for instance, let's say we have these polygons are similar. It wants us to find the perimeter of each polygon. Well, this polygon's not too bad to do. The perimeter is just adding up all the sides. So this polygon's perimeter over here, we'll call this again A and B. This polygon's perimeter is simply 9 plus 8 plus 7 plus 10. Let's do that real quick. 9 plus 8 plus 7 plus 10. 34. So one down. This polygon's perimeter is, well, I don't know. I have a 4, but I don't have any other sides here to add. So this one I'll just call x. I don't know what the perimeter is. But I can find it out using my scale factor trick again. So for instance, if we look at the similarity statement here, I know what wx is, right? wx is 4. So here, I know that wx is 4. So I know the first and the last letters, that side is 4. What would that correspond to over here? Well, if I did wx, that means that should correspond with qm, because again, the letters are in the same arrangement there. So qm is 8. So 4 and 8 are corresponding pieces, which means they make a scale factor. So I can do 4 over 8, which is 1 over 2. That's my scale factor. And I can set up an equation to solve. So I have 1 over 2. Again, that's A over B. 4 is part of A, 8 is part of B. Is equal to this other scale factor, or sorry, this other fraction, which is going to be based on the perimeters. So what's the perimeter of A? I don't know, so x. What's the perimeter of B? Well, that I do know, and that's 34. So 1 over 2 is equal to x over 34. I can then, once again, cross multiply. There's actually a quicker way you could do this, but I'll leave that for you to figure out if you want to figure out some shortcuts. And then divide by 2, just so I don't have to pack too much in this video here. and we end up getting 17 is equal to x. So the perimeter of the small polygon is 17. So without even knowing all the sides here, as long as I know a similar polygon in that perimeter, I can set up a scale factor and solve for the perimeter of this other polygon. And again, this all revolves around getting that correct scale factor first, and then using that to set up some ratios and cross multiplications to solve for any other sides that you need. So again, I'm not going to go through these two here, but the labeling here is pretty darn important. So like if you're doing this problem right here, number 4, if I said where are some corresponding sides here, corresponding sides means they fall in the same order. So like JK would correspond with TS. First and second, first and second. KM would correspond with SQ. So KM could be another one you make. KM would correspond with SQ. So corresponding means that you can use them to make a scale factor. So if I said make a scale factor, you could take JK's number divided by TS's number, and that will give you a scale factor. Or you can take KM's number and divide it by SQ's number, and you still get the same scale factor. Now, KM and SQ are diagonals, so they're a little bit weird, but they could theoretically happen. And then same thing with LM and RQ and QT and MJ. As long as they're in the same order of the polygons, we can use them to create a scale factor. So again, if we want to check if they're similar polygons, we have a few methods here. Like in this case here, determine whether each pair of figures is similar. Well, for number 6, we automatically know that they're similar because of the angles. They have 2 sets of congruent angles, at least. I mean, they actually have 3. But these triangles have 2 sets of congruent angles, therefore they are similar right off the bat. If you want to, you can check the sides. 6 times 2 is 12, 4 times 2 is 8, 3 times 2 is 6. And you could do that way. But for triangles, as long as you know that the angles pairs are congruent, then the polygons are similar right off the bat. For rectangles, you may have to check it a little bit. So like for a rectangle here, you want to check to see, okay, is small piece to small piece, so 4 is the smallest piece in rectangle A, 9 is the smallest piece in rectangle B, is that the same order as large piece to large piece? So is 4 over 9 equal to 10 over 18? Do these give me the same decimal? Well, if you check, 4 over 9, is that the same as 10 over 18? No. So these would not be similar, okay? These would be no, because these come out to be different decimals, okay? So that's, again, you have 2 ways of checking if they're similar. For triangles, check the angle pairs if you can. If you get 2 matching angle pairs, the triangles are similar. For other polygons, you need to check the sides there. I think I might have said earlier in the video that this angle trick works for all polygons. It doesn't. I might have misspoke there, so that was my apologies. This angle trick only works for triangles. It doesn't work for, say, rectangles, because obviously you have matching angles in rectangles, but they're still not similar. So the angle trick you only can use for triangles. For all the other shapes, you need to go ahead and check their sides and make sure that you have a corresponding or a constant scale factor between all the pieces. Now, this one here says the polygons are similar, find the value of x. Again, this is just the same thing we were doing at the beginning of the video. Like for number 7 here, if I want to find x, I need to get a scale factor. Well, use the angles to help you out. 4 is between the single arc and the double arc. 8 is between the single arc and the double arc. Ergo, that's going to be your scale factor, 4 over 8 or 1 over 2. And then if you want to find what x is, you would do 1 over 2 is equal to, again, I did a over b for my scale factor. So it'd be a over b, 3 over x. And then you'd cross multiply and you get x is equal to 6. Now you could also do that in your head mentally once you know it, because you can say that, okay, well, to go from 4 to 8, that's timesing by 2. Ergo, to go from 3 to 6, I'm also going to times by, or to go to 3 to x, I'm also going to times by 2, which means x has to be 6. So if the scale factor is nice enough, you can actually kind of do that in your head. If it's a little bit messier of a scale factor, like 3/7 or something like that, then you might want to set up a fraction. But again, that's your own preference there. Number 8 is a very similar problem, so I won't necessarily bother you with that one there. So I believe, yeah, that's the end of this video here. If you have any questions or so, please email me, let me know. But again, this was just kind of go over the algebra of similarity, and then we'll go over the proof stuff of it in the next video. Hope you enjoyed this video. Hope to help you out. Have a good day.